In this video, we're going to be looking at factoring a perfect square trinomial. So the first step to factoring is always finding the greatest common factor. That doesn't change at all. Okay, so you're going to look for greatest common factor. Sometimes there is one, sometimes there is not one. The second step is dictated by the number of terms. So in the last video, we looked at a difference of two squares. That can exist if there are two terms. In this case, we're going to be looking at situations where there are three terms, and if there are three terms, perhaps we could factor it as a perfect square trinomial. So a perfect square trinomial is in the form a plus b squared or a minus b squared. And that would be the form factored. Before it's factored, it would look as a squared plus 2 times ab plus b squared, or in the case of the difference, a squared minus 2ab plus b squared. Okay, and you can see this, you could verify this if you took a plus b and you expanded it. So it's a plus b times a plus b, and you distributed all of this out. You're going to see that once you distribute it out and you combine like terms, it is going to look like what we have over here, a squared plus 2ab plus b squared. And the same thing is true for the difference. So let's take a look at how to factor this. So in example A, we have x squared minus 10x plus 25. So we already have a base of x that's being squared. So that means our a in this case is going to be equal to x. The last term, 25, we can rewrite that as 5 squared, which means that b would be equal to 5. And notice if we multiply a times b together, we get 5x. And then if we double that, we get 10x, which is equal to our middle term. That is telling us that we can factor this as a perfect square trinomial. So this will be equal to a minus b squared, and I'm using the minus sign there because I have a minus sign in my trinomial. And our a is x. I'm going to put it in parentheses because I always substitute in parentheses, even though sometimes it gets a little clunky looking. And our b is 5 squared. Oh, excuse me. Let's backtrack. I put that exponent of 2 in the wrong place. In both cases, the exponent of 2 should be on the outside. Excuse me. So I'm going to rewrite this as x minus 5 without all these clunky parentheses, since we really don't need them in this case. So this would be our answer in factored form. And we could do a quick check. If you're factoring, this is something that I tend to do in my head, not so much out on paper. So we have x squared minus 5x plus 25. So this is x squared minus 10x plus 25, which is what we started with. Okay, let's look at another example. So we have 16x squared plus 24x plus 9. So again, notice we can rewrite 16 as 4 squared. And we could rewrite 9 as 3 squared. So this first term would really be 4x squared plus 24x plus 3 squared. Our a then would be equal to 4x. Our b would be equal to 3. If we multiply those two together, we get 12x. If we double that, we get 24x, which matches our middle term, which means that this is a perfect square trinomial, and we could factor this as a perfect square trinomial. So this would be 4x plus 3 quantity squared. And again, you can expand this to double check that we get 16x squared plus 24x plus 9. And I like to check this in my head. Okay, if you could just square 4x, you're going to get 16x squared. Square 3, you get 9. That's the last term. If you multiply those two together and double it, you get the middle term. So this would be our answer in factored form. And before we go, let's take a couple of examples that are not perfect square trinomials. Let's look at y squared minus 15x plus 36. So we already have y squared. We could rewrite 36 as 6 squared. So that means our a would be equal to y and our b would be equal to 6. But if we take that y and that 6 and we multiply it together and double it, we end up with 12y. Excuse me, I got to backtrack again. I have x's and y's in here, which is going to make life a little bit more complicated than necessary. So we have all y's. So if we take our a and we multiply it times our b, we get 6y, and we double it, we get 12y. That does not match our middle term. Therefore, this is not a perfect square trinomial, which I often abbreviate as PST. That doesn't mean that we can't factor this, but we can't factor it as a perfect square trinomial. And we'll look at one more. 9x squared plus 42x minus 49. So here we can rewrite 9x squared as 3x squared. That's a perfect square. We could rewrite 49 as 7 squared. So it looks like a is 3x and b is equal to 7. So we might be tempted to write this as 3x minus 7 squared. Because even when we check, we multiply a times b together, we get 21x, and we double it, we get 42x. So it certainly seems like this is a perfect square trinomial. But what we're going to find is if we factor this as 3x minus 7, if you go to check this and you expand this, you're going to get 9x squared minus 42x plus 49. Notice the signs do not match. So this is not factored properly. If we try to factor this as 3x plus 7 squared, when you go to check this and you expand it, again, you're going to find that the signs do not match. We're going to get all positive signs here. So the signs actually matter. If we go back and we take a look at the signs for a perfect square trinomial, let's go to the very top at the notes section. Notice both terms have to be positive. Well, I should say the middle term and the last term have to be positive, and we could factor that as a binomial squared that has a plus sign in it. If the middle term is negative and the last term is positive, then we could factor that as a binomial with a minus sign in it. Those are the only two cases. If they are both minus signs, or the last term is a minus sign, as in this last example, this is not a perfect square trinomial. Okay, so the last term cannot be negative. And I'll let you think about why that is true.